Okay, hey guys, welcome back to the channel. So this is the next chapter in the chemistry syllabus, which is carbonyl compounds, specifically about aldehydes and ketones. So in the last video, we talked about alcohols and how they can be oxidized to form aldehydes and ketones. And let's talk more about their structure and their chemical reactions. So we covered that in this video. And as usual, I hope you guys have been enjoying the videos and you've been finding them useful and you learn something. And if you do have any questions, leave them in the comment section and maybe I'll get back to you as soon as possible, or one of your friends or one of the other users of the YouTube channel could get back to you as well. Okay, so let's finish this chapter out. It's a very short chapter. There aren't many reactions, and it has one new mechanism. So that's the main thing that you need to focus on. Okay, let's carry on. Okay, so the structures. Aldehydes and ketones are called carbonyl compounds because they have the carbonyl group, which is a C double bond O. Ketones have this structure of R2 C double bond O. Aldehydes have a CHO bond, which is C double bond O H. The R over here for ketones, it can be anything. It can be, say, CH3, it can be a H, it can be anything. And then for naming them, so we consider the longest carbon chain as per naming of other organic compounds. So for methane, you just need to take note of the total number of carbons, total number of carbons in the compound or the longest carbon chain. And then for aldehydes, you have to add a al, and then for ketones, you have to add a on. So propanol will be CH3, CH2, CHO. So this is the CHO bond of aldehydes. And then ketones will be propan 2-on. So 2 over here signifies where the double bond O is. For propan 2-on, there can be only one. So for compounds with more than 3 carbons, there can be on multiple positions. For example, pentane, or sorry, 5 carbons, then it'll have on the second and third carbon. Yeah. Okay, so let's move on. So formation of aldehydes and ketones, so we discussed this in the alcohol chapter. So we can form them from oxidation of alcohols. As we know, aldehydes can be oxidized from oxidation of primary alcohols, and the O over here represents the oxidizing agent, which we know as 2E, K2Cr2O7, which is also acidified with H2SO4. And to obtain the aldehydes, you have to heat and distill them. So carboxylic acids are not formed from full oxidation. And distillation can be done because aldehydes have a lower boiling point than alcohols. And let's talk about ketones as well. So they're formed from secondary alcohols. And the conditions for this is heat under reflux and is the same reagents. And do take note for the color change for this. It's orange to green, and its colors come from the complex ions of Cr2O7 to minus and Cr3 plus. So it goes from orange to green, which is reduced, and then the alcohol is oxidized. So the reaction of aldehydes and ketones. Next part we need to talk about is reduction. So we talked about oxidation, let's talk about reduction. So if we reduce an aldehyde, we'll go back to what it was oxidized from, which is the primary alcohol. And same for ketone, which is go back to secondary alcohol, correct? So the reagents which you can use for this is LiAlH4 dissolved in dry ether, and the conditions are room temperature. So we've also seen this reagent and condition for reduction of carboxylic acids. And then there's another alternative reagent condition which we use only for aldehydes and ketones, which is NaBH4, and conditions are heat and warm. And then just take note that LiHH4 can also be used to reduce the CO2H, but also but not NaBH4. Okay, so these are just some reactions on how the reaction happens. So I'll just read you one for propanol, for example, which will take it back to propan 2-ol. Okay, so CH3, COCH3, and you add 2 hydrogen. So the hydrogen adds to the CH, the double bond O breaks, and then the H is added to the O. So it goes back to the secondary alcohol. Okay, and it's the same type of reaction for the aldehydes. You have to just form back the primary alcohol, the CH2OH group. Let's move on. So the new mechanism that we're learning in this chapter is called the nucleophilic addition with cyanide ions, which is a nucleophile in this reaction. So first thing to do is we draw this entire compound. So these two arrows indicate whatever. For example, it can be H or R if it's aldehyde or ketone. So if it's sorry, so if it's aldehyde, that'll be a H here, or if it's a ketone, it'll be two R's, with R being any alkyl group like C2H5 or CH3. So what happens here is that there's a double bond, sorry, there's a lone pair. So you draw the arrow from the lone pair to the carbon, which is partially positive, and the oxygen is partially negative. So the double bond breaks and then it goes to oxygen. So you produce an intermediate. There's a bond between the C of the compound and the cyanide ion, and then the this O gets a lone pair and it becomes negatively charged. So the oxygen here, it will basically form a bond from the lone pair to a hydrogen, which is present in the HCN molecule. So this molecule is produced. So we'll talk about the reagent condition in a bit. So it forms a bond to the H, and then this bond will break and produce a cyanide ion, cyanide minus ion over here, and then you produce the compound here with CN and OH, and these two can be variable as we've been discussing. And finally, you'll also produce a CN minus ion, which can again take part in the first step. Okay, so if you don't get it, just pause here for a second and just look at this diagram. You just need to draw these steps if they ask you to show the mechanism of nucleophilic addition. So the conditions for this is HCN, which is formed in C2, meaning it's formed within the reaction using NaCN and WH2SO4. So NaCN catalyzes the reaction. So the CN minus ion is the catalyst. Also, it also acts as a catalyst and the reagent. The conditions: heat under reflux, type of reaction is nucleophilic addition, as we were discussing, and CN minus ion is a nucleophile because it donates a lone pair of electrons. So let's just go back here for a second. So see over here, the lone pair is being donated to this partially positive carbon. Okay, so we also need to learn how to name nitriles. So first, we look at the longest carbon chain. But since a nitrile is adding another carbon into the compound, we have to consider the carbon added from the nitrile as well. So, okay, so this is propanol, right? So you add the HCN, you form the CN and then the OH. So what happens is now that you have 4 carbons in the full compound. So this becomes butane nitrile. And for this compound, the OH bond over here is no longer the main functional group. It's not present in the main longest carbon chain. So this will become a side chain. And when OH group becomes a side chain, it's called 2-hydroxybutane nitrile. So just take note, whenever you're naming nitriles, you have to consider the carbon added from the CN as well. Sorry. So there's also another reaction of nitriles that we need to know, which is hydrolysis. We already talked about this in the previous lessons, but again, you can reflux the nitrile with dilute HCl, and then you add H plus and H2O, which will produce COH and NH4 plus. And you can also reduce it to an amide, which is Na and ethanol. Although I've not seen this being tested, it'll be good for you to learn it, although it's mostly more applicable towards the A2 syllabus. So CN plus 4H, sorry, will give you CH2NH2. This is the, sorry, this should be an amine, not an amide. That'll be a mistake here. Just note that this is an amine or amide. All right. So the next part we need to know is testing for carbonyls. So testing for carbonyls can be used by 2,4-DNPH and also using Collins and Felling's reagent. So the first thing what we can talk about is 2,4-DNPH. So if an aldehyde or ketone is present, a deep orange PPT is formed. So you don't have to memorize this structure. It'll be good if you can remember it, but I think you can just shorten this to NH, NH2, and then you can just make this entire thing R. So what you need to know here is that this H2O, H2 from N and O, which is part of the C double bond O in the carbonyl group, they break off and then they form water. So this is a condensation reaction. So it forms water, and then this N and C, which is left over, they form a double bond. Okay. So let's differentiate between ketones and aldehydes. So we know that aldehydes can be further oxidized to form carboxylic acids, but ketones is the final step of the oxidation reaction. So we can add mild oxidizing agents, and then we can see the difference. So one of the reagents is tolerance reagent, which is an aqueous solution of silver nitrate in excess ammonia solution. So it contains Ag plus ions, which act as the oxidizing agent. So Ag plus will be reduced to Ag. So the observation we see when the oxidation reactant occurs, or when you add aldehydes to tolerance reagent, is that a silver mirror is formed at the bottom of the test tube. But there's no change with ketones, because ketones can't go any further oxidation. And for Fellings, it's a alkaline solution containing Cu2 plus ions, which act as the oxidizing agent. So when aldehydes are added to the Felling solution, or Felling solution is added to aldehydes, it is reduced to Cu plus ions, and the blue clear Felling solution will turn orange red. And then there's no further reaction with ketones with the same explanation that ketones cannot go further oxidation. Lastly, there's also a test for the methyl ketone group, which is the CH3CO, C double bond O. So the test for methyl ketones can be done when the CH3CO group is present, CO group is present, but it also can be for CH3CHO, which is also containing the CH3 C double bond O group. It can also be for some secondary alcohols when it becomes oxidized to contain the methyl ketone. So just remember that in the end, it must contain a methyl ketone after the oxidation or whatever. So what we need for this reactant is NaOH and iodine. And then the observations are yellow PBT, which is from CHI3, which is formed during the reaction. Although I've not seen this reaction pathway being tested, mostly they test what is produced at the end, which is just giving the name of triiodomethane and CHI3. I'll just read this out for you so that you can understand. So in the first step, the H3 is replaced by iodine. So it becomes RCOCH3 to RCOCI3. Then this RCO becomes a carboxyl group, so RCO minus and Na plus, and the CI3 accepts the hydrogen and becomes CHI3, which is formation of triiodomethane, which is the result, which forms the yellow PPT at the end of the reactor. Okay, so this is what I've been talking about some secondary alcohols. So CH3CHOH, when it becomes oxidized, it'll contain what? The methyl ketone. So it'll also test positive for this test. So that's the end of this entire chapter. It's a very short chapter. It contains only a few reactions. So let's just cover some questions to test your understanding of everything. So let's talk about this question. So propanol will react with hydrogen cyanide to form 2-hydroxybutane nitrile. A suitable catalyst for this reaction is sodium cyanide. What statements about this reaction of propanol with hydrogen cyanide is correct? So let's talk about the first option. The cyanide minus ions attacks the propanol molecule to form an intermediate ion. Yes, this is true because the intermediate ion will contain the CN and O with the lone pair minus. So it will contain an intermediate ion before the O will accept the H to form OH. Then the product of this reaction will contain a chiral carbon. So yes, this is true because look at this carbon right here. So this carbon is bonded to 4 different groups, namely H, OH, CN, and then this entire group of C2H5. So 4 different groups, definitely a chiral carbon. Lastly, so CN minus ion is a stronger electrophile than the HCN molecule. That's wrong because in this reaction, it's nucleophilic addition. So CN minus ion will act as a nucleophile, not an electrophile. So the answer for this would be 1 and 2 or B. So this next question, which compound will react with acidified potassium dichromate and with alkaline aqueous iodine? So acidified potassium dichromate, it's an oxidizing agent. So first of all, it must undergo an oxidation reaction. And secondly, alkaline aqueous iodine, that's the triiodomethane reaction. So it must contain a methyl ketone. So the first over here, CH3CO, CH2CH3, this will not go oxidation. This is a ketone. So ketones cannot go any further oxidation. So this is wrong. This over here, CH3CHOH, CH2CH3, this is a secondary alcohol, can be further oxidized to form a ketone. And it does form a methyl ketone. So if you draw the structure over here like this, a double bond O will form at the second carbon. So this is a methyl ketone. So B is the correct answer, but we will discuss C and D as well. So C, this is an aldehyde. It will go for the oxidation, but it will not produce a methyl ketone. It will produce a COH. So C is definitely wrong. And lastly, D, so this will also go under oxidation, but it's a primary alcohol. So the final product would be a COH. So the answer is wrong. It's the same explanation as C. Okay, let's carry on. Okay, so the formula of three compounds are shown: C3H7CHO, C2H5COCH3, CH2CH, CH2CH2OH. So let's talk about the functional group before talking about all of this. So this one contains an aldehyde. This contains a ketone, and over here, if you look properly, this is a alkene, and this contains a primary alcohol. So only one of these compounds will decolorize bromine water, and only one of these compounds will produce a silver mirror with tolerance reagent. So what decolorizes bromine water? Alkenes, and then what will produce a silver mirror with tolerance reagent, something that can go mild oxidation, because tolerance reagent is a mild oxidizing agent. So this is an aldehyde. So let's talk about all these options. So decolorizes bromine water must be an alkene. So definitely A and B are, because this is aldehyde, this is a ketone. So these C and D is possible answers. And then let's talk about forms of silver mirror with tolerance reagent. It can only be an aldehyde. So only B and D are possible answers. So finally, you can cancel out C and then A and B. So the final answer should be D. All right. One last one. So compound X, CH3CHOH, CHO, CH3 is heated and under reflux with excess acidified K2Cr2O7 to form a compound Y. So X undergoes an oxidation reaction to form compound Y. Both X and Y are separated by warming with Felling's solution. So what this is testing is differentiation between aldehydes and ketones, and the first part is an oxidation reagent. So let's draw the structure here. So if you draw this out, let's talk about the functional groups. First of all, secondary alcohol, and last one here, yeah, that's aldehyde. So what will happen if it goes under an oxidation reaction? Secondary alcohol becomes a ketone, and CHO becomes further oxidized to form a COH. So basically, if X and Y are separated using Felling solution, what would be the observations? So if you use Felling on X, a red precipitate will form because of presence of an aldehyde, but Y, it will not form. Okay, just give me 1 second. Yeah, so sorry, I just got confused for a second. So Y will not form because over here this is a ketone, and then this is a carboxylic acid. So ketone cannot go under further oxidation, and C11OH cannot go under further oxidation as well. Sorry, I just got a bit confused by the phrasing over here. That will be my bad. So I hope you understand this question. This written part text here also has an explanation if you didn't understand my explanation for this question. Overall, okay, so that'll be the end of this chapter, carbonyls. So I hope you have understood everything. If you have any questions, leave them in the comment section, and I hope you found this video helpful. Do consider subscribing and liking the video and sharing it with your friends so that more people can benefit. Until then, I'll see you in the next video. Happy learning.